So the first day, what we had done was we'd gone back and talked about some previous stuff from geometry that would be kind of foundational to what we're going to be doing this first semester in trigonometry, right? I'd like to take a few more minutes here and run through some more kind of just specific numeric example problems. We'll do that for a bit. We'll stop, take a break. We'll do some practice of those kinds of problems using delta math. I think some of us may have already done the delta math assignment. That's okay if you have. We'll get that going. We'll take some time in class to do that. And then we'll start chapter 1 from the trig book. Okay? All right, cool. So, just some more geometry review. So we're just going to take a couple of example problems here. So if we're just solving for x here, we have a right triangle where angle B is 37 degrees, side AC is 13, and side CB is x. What do I need to use to solve something like this? Yeah, I need to use SOHCAHTOA, specifically tangent. How did we know it was going to be tangent specifically? Oh, you looked at your notes. Okay. We'd start by looking at the angle measure we're given. Relative to that angle, the sides we care about are opposite and adjacent. So we know that we should be using tangent from SOHCAHTOA. Everybody's okay with that? Okay. So the equation that I would write then would be tangent of 37, always the angle measure inside sine, cosine, or tangent, equals the opposite in this case was 13, and the adjacent was x. Geometry is now finished. It's algebra time. So to get the x by itself, what should I do first? Multiply both sides by x. Thanks, Braden. So I'm going to have x times tan 37 equals 13. And then to get the x by itself completely, divide by tan 37. Remember, tan 37 is just all one number. That's something you could type into your calculator. You get like a kooky decimal or whatever, but that's just something that we would type into our calculator. Before we go ahead and do that, when we're using sine, cosine, or tangent with our calculator, what do we have to be careful of before we start doing that? Yeah, we have to make sure we're in degree mode. So if you turn your calculator on, check that. We'll press the mode button right next to the blue second button. The degree part should be highlighted. If it's not, just use your arrows to go highlight the degree and press enter. Okay. And so to type this in, I like to use the fraction option. So if you press alpha and y equals, that'll open up the fractions menu. If you select fraction option number 1, you'll get the vertical fraction, so you can type this in just like it looks on your sheet of paper. While for this problem, it didn't particularly matter whether you did this in like as a fraction or just with a division sign. It's not a big deal. Oftentimes later on as we go, this will make things enormously easier to type things in because you don't need a million sets of parentheses. You can just type it in exactly like it looks like on your sheet of paper. But I'll use that shortcut a lot. So here we get 17, yada, yada, yada. If I want this to the 100th, how would I round that? 17.25. If I wanted it to the 10th, I would round it as 17.3. Oh boy. And the only reason we're talking about rounding it two different ways, I think when I used when I ran through the delta math, frequently they're going to ask you to either round things to the, 100th or 10th or ask for it exact. Okay, so just as we do these things, when it's appropriate, I'll ask for things a couple of different ways so that just to remind you guys of what to do with that. Everybody's cool? Next one, let's do, say, so for this one, we have triangle ABC. It's a right triangle. We're given that angle B is X and side BC is 7 and AB is 12, and we're asked to solve for X. What are we going to use here? Cosine. So again, sine, cosine, or tangent. Specifically, this time we'll be using cosine. Why? Because relative to the angle that we're given, we know about adjacent and hypotenuse. Excellent. Everybody's cool? So the equation we'll set up is cosine of X equals adjacent, which was 7, over hypotenuse, which is 12. Great. So far, so good. To solve for X, we got to get rid of that cosine in front of the X. What gets rid of a cosine? The cosine inverse. Very good. So we'll do cosine inverse of both sides. Just as an aside, I'm not multiplying by cosine inverse. Cosine inverse is not a number that you can multiply by. It's an operation. It's like doing the square root to both sides. We're doing the cosine inverse to both sides. Everybody's okay with that? Again, I know what you mean if you say multiply both sides by cosine inverse, but it's not correct. And again, communication is one of those kind of like soft mathematics skills that I'd like to continue to work on with you guys. It's not something that we assess, but it's something that we should try to do a good job of being precise and saying what we mean. All right, calculator time. So to get the cosine inverse, I press second and then the cosine button, and I can do fraction 7 over 12. So I get to the 100th, I would say this is 54.31, and to the 10th, I would say 54.3. What might I, if I was being really picky, object about those two answers you've given me? If I was being really picky, what could I quibble with about those? Yes, sir. Not saying degrees, yeah. So those are angle measures. Remember, we always get an angle measure back from an inverse trig function. From a regular trig function, you get a ratio of side lengths that has no unit to it. But a inverse always gives you back an angle measure, so we should be specific and say that these are degrees. Now, am I going to grade you down for that? No, but as long as we're talking, these are things that I like to harp about and we'll pick on only in conversation. I wouldn't grade you down for doing something like that. Unless the directions explicitly reminded you to, like, you know, make sure to represent all angles with degrees or radians or whatever. Because there will be cases where we'll be using back and forth between them, and there it's important you're indicating which one you're using. In this, though, obviously we're doing degrees. Because we haven't even talked about what a radian is yet, even if you remember what that was for geometry. Okay. What if we asked for, say, let's say we have no, I don't want that. Let's do, I could do that still. Do that. And then I'm just trying to make this work out the way I want it to. Sorry, hold on. I'm going to have it 46. That'll do. Okay. And then we'll say A, B, C. And let's say we want the value for cosine of A. All right, so you're given a right triangle ABC where side BC is square root 35 and side AC is square root 46, and we're asked to find the value for cosine of A. So we're using cosine, right? First thing to do is locate angle A. Cosine is adjacent over hypotenuse. The adjacent side is square root 46. The hypotenuse is obviously AB. So we're going to have square root 46 over, well, let's call this x for now. We need to figure out what x is. How can I figure out what x is?
Wait, I had it. Wait, come back. You can ask it.
Okay. How can we figure out what x is? Yeah. Pythagorean Theorem. Yeah, if we have no angle measures, but we have two side lengths, Pythagorean Theorem is way to go. When I do the Pythagorean Theorem and we're plugging the numbers in for A, B, and C, what do I have to be careful about? Braden? That the hypotenuse is C. Yeah, very good. So A and B, which one is which, doesn't matter. So what's the nice thing about this? Yeah, the squareds and square roots cancel out. So we're really just left with 35 plus 46 equals x squared. So 81 is equal to x squared. What do I do next? Square root both sides. When I square root both sides, what do I get? Plus or minus. Now, do I really need a plus or minus in this context? No. Why not? Excellent, because a side length can never be negative, right? It's the length of a physical object. Negative side length would make no sense at all. So I'm not going to bother with the plus or minus in this context, but I want to remind everybody that when we square root both sides of an equation, we have to worry about that. Everybody's happy? So my final answer here, depending on the directions, would be cosine A of square root 46 over 9. Now, if it asked for this rounded to 2 decimal places, what would I do? Just type that garbage into my calculator, right? Or to 1 decimal place or whatever it asks for a rounded answer. That's no big deal. So fraction command, square root 46 over 9. So 0.75-ish. Everybody feel good? No big deal? Does this kind of come back to you, more or less? Good. I'm going to pause the recording right now because we're going to take a few minutes and, oh, Chanel.
Oh, sorry.
That's okay.
So do you put cosine for 46 over 9?
No.
Or,
because this was asking for the value of cosine.
Okay.
So
yeah, no, okay.
So if we wanted to solve for angle A, we would take the cosine inverse of both sides to find angle A. This is just asking us for the value of cosine.
Oh, okay. Thank you.
Is that good? So subtle difference there, right? In terms of like where to go, where to stop.
Oh, okay. Yeah, thank you.
Sure. So again, I'm going to pause the recording right now because we're going to take a time out and let you guys work on some delta math problems relating to this topics. Okay? So, chapter 1 is going to be like our Algebra 2 review, because as we talked about on the first day, this is a little bit of a mashing of Algebra 2 skills and geometry skills, kind of as our foundation. So we've done a little bit of geometry review, and we'll kind of continue to spice that in when necessary. But chapter 1 is really a review of Algebra 1 skills, okay, or Algebra 2 skills, excuse me. There might be Algebra 1 skills kind of scattered in here too, depending on how thorough or abstract of a job your Algebra 1 teacher did. So the first section in chapter 1 is all about functions. Does anybody remember the definition for a function? Braden? Oh, Drew?
It's like looking up x with exactly 1y.
Sure, that's a reasonable working definition. I'm going to be a little bit more precise when I do mine, because there's some nomenclature I want to add in, but that's perfectly workable definition. Gives you great intuition about what a function is. So we'll say that a function from a set D to another set R is an assignment or matching or pairing or mapping. I'm going to call it an assignment, such that every element in D maps uniquely to an element in R. So this set D, we call that the domain. And this set R, we call the range. So domain are the inputs to your function, and the range is the outputs for our function. Everybody kind of jogging their memories? So let's think about, like, visually, what is this really saying? So let's draw like a mapping diagram representation of our function. So this first circle is going to be our domain. This circle is going to be our range. So that's going to represent our sets D and R. And from the domain, I need every element in there. Let's say I have 3 elements. Needs to map to exactly 1 element in the range. So that would be like what the function looks like, right? This would be some function f or whatever. Okay, I'm going to draw a couple more mapping diagrams, and you guys will help me decide whether these are functions or not. Sound okay? Again, this is probably Algebra 1 or definitely Algebra 2 review. Okay, let's see. Is that a function? Yeah. All the x's go somewhere, and they're only going to one place. Does it matter that all the y's aren't hit? Nope, it does not. Everybody's cool? Okay. Call that B then. Is this a function? Why not? Yeah, one of the domains doesn't have anything, it's not going anywhere. Everybody's okay with that? In the parlance you guys would be familiar with, if that was like, if again this was f and this was like x1, like f of x1 in this case would be undefined. Because that x doesn't go anywhere. There's no definition to it. Right? Is that okay? We talked about undefined things before. That would be like what's going on there. C, we'll do one more example here. Is that a function? No, what's the problem? Yeah, we have 1x that's going to 2y's. Right? So that would be like saying that f of 1 equals 2 and that f of 1 also equals 3. Something like that. And that's a problem because when does f of 1 equal 2 versus when does it equal 3? Does it equal both at the same time? It's all very like ambiguous as to what's going on, what that would even mean, right? Everybody's okay? So that's bad. Guess we forgot to write no up there, didn't we? Okay. Now, how often did we actually represent our functions using a mapping diagram? Like never, right? That's not something we really did. What's the most common way we represent a function, like in your Algebra 2 class? With an equation, right? So let's look at some equations. So y equals x squared plus 2. Is that a function? Okay. Mary, you were shaking your head yes, right? You say yes? Okay. Can you tell me why? Okay. Does anybody else think it's yes and has an explanation to go with that? So if you look at this, does this remind you of a kind of function you studied in Algebra 2? What does it look like? Pierce. Okay, so the graph of this would look like a parabola. It's a quadratic equation, right? And we know that quadratic functions are functions. So you could just tell by looking at this that it's a function. You could also say that I know the graph of it looks like a parabola. And then if I know what the graph looks like, how can I tell if something's a function or not? The vertical line test. What are we looking for on the vertical line test? Yeah, can I draw a vertical line that intersects the graph in more than one place? Clearly for a parabola, any vertical line I draw is only going to intersect it once. Everybody's okay with that? So the answer is yes then. Everybody agree? I would say there wasn't enough information given to determine. So I would say that the answer here is yes. If we are specific, yes, y is a function in terms of x, where if we assume x is the independent variable and y is the dependent variable, then yes, this would be a function. But what if what if it was the other way around? So you could have also answered no, that x is not a function in terms of y. What would our explanation there have been? Well, I would say that if y is equal to 3, then x could have been 1 or -1, right? Negative 1 squared plus 2 is 3. And so is positive 1 squared plus 2 is 3. Now, that's a little bit of an unfair of Mr. Kulik to do, because in your algebra 2 situation, when we wrote y equals x squared plus 2, x was always assumed to be the independent variable, right? Everybody agree with that? Is there a different way that I could have written this to make it crystal clear that x had to be the independent variable, that x was the domain set? What? Yeah, so if I wrote this as f of x equals x squared plus 2, here clearly we're saying that f of x is a function in terms of x. We're crystal clear that x is the input, f of x is the output. In that case, undeniably that's a function. And you could have said that because you recognize that it's a quadratic function. It's a class of something I already recognize as a function, because it's in the form ax squared plus bx plus c. Or you could have said, okay, the graph of this is a parabola. That passes a vertical line test. So that's a function. Either of those two explanations, perfectly fine. But we do need to be a little bit careful when it's written as y equals yada, 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 that the directions will tell you, is it a function of one variable in terms of the other? Everybody's okay? Let's do a couple more examples just to clean this up a little bit.
Thank you.
You're welcome. So let's say we have x squared plus y squared is equal to 1. And maybe we'll ask, is x a function, let's say, is y a function in terms of x? So there's like 3 or 4 different ways you could justify your answer to this. Let's start with the first, is it a function? Does anybody have any intuition about that? Okay, that's fine. Nobody does. Okay, what can we try to do then if we don't have any intuition just by looking at it? Plug in some numbers. Great. So what would be good numbers to start with? Let's pick a number for x. What would be a good number for x that we maybe start plugging in? 2, okay? So 2 squared, let's write this way, x equals 2. So that's going to give us 4 plus y squared is equal to 1, right? Everybody agree with that? So y squared would have to be negative 3. Well, that can't happen. That's okay that that can't happen, because what we probably mean by this is for the domain of the function, we probably are just talking about the domain being the values for which x is defined, right? That was pretty common assumption when we were in algebra 2. Everybody's okay with that? Like, we didn't say that 1 over x is in a function because x equals 0 is undefined. We just said the domain for that function just didn't include 0. So 2 was probably not a great guess. But let's try, should we go bigger or smaller? 1. Let's try 1. Okay? So x is 1. Oops. So y would have to just be 0, right? Well, that seems okay. You convinced yet that it's a function? You shouldn't be. Let's pick another value. Who whispered 0? Did somebody whisper 0? Nobody wants to take credit for that? I heard somebody whisper 0, I thought. That would be a good one to try. So when we square root both sides, we get 2 y values. So no, not a function. Everybody's okay? So we just played around with it a little bit, and we found that, yeah, there are some values for x. They give me 2 y values. They can have 2 y values for it, right? Does that all make sense? What else could have you done here? You could have tried to graph this on your calculator. Now, the way it's currently written, can I graph this on my calculator? What's the problem? The y squared, right? The y is not by itself. So to rearrange this to get it into a form you can type into your calculator, you'd have to get the y by itself, so we subtract the x squared over. We square root both sides. And now that's a little bit of a problem, right? What's the problem with this now? The plus or minus. We can't type a plus or minus into our calculator. So what we would just want to do, oops, I pressed the wrong thing there. That's a bummer. Sorry, I opened this big program that's going to close. Okay. So to do this, what I can do is I'm just going to do this in 2 lines on my calculator. And I'm just going to go down and make sure that nothing else is set to graph that I don't want. I'm going to look at my window and just shrink that down a little bit. And I have my axes off. Aha! What do we got here? Looks like a circle, doesn't it? Okay. So like fails a vertical line test, right? Okay, good. And then what's the third way we could have recognized this? It's a geometry thing. The equation for a circle was x minus h squared plus y minus k squared is equal to r squared. And that represents a circle with center hk and radius equal to r. So I could say that x squared plus y squared equals 1 is a circle with center 0, 0 and radius 1. Oh, I meant to write a 1 there, r there, not a 1. And I know that a circle obviously fails a vertical line test, right? Any of those explanations, super valid. All of them are great. Whether you recognize that as the equation for a circle right off the bat, whether you recognized it as something you can rearrange and graph on your calculator, or if you just like, I'm just going to kind of play around and plug some values of x in and see if I can get 2 values of y to pop out of that. All of those are appropriate. Everybody's okay with that? In particular, if you're looking for functions of y in terms of x, if you rearrange them and can get a plus or minus in there, it's pretty easy at that point to come up with 1 value of x to give you 2 values of y. All you need to do is get a non-zero number in there somewhere, and you should be good. Is this feeling okay? So we talked about a bunch of different ways you could have approached that, which I think is often super helpful. To like, here's some tools in my toolkit. Any of these approaches are fine. Oftentimes, some of them are easier than others. Some of them are like, how much do I know? And I can just recognize on sight what this is, versus like, I just need to kind of play around with it until I can get it to work. Okay. So that's basically 2.2 or 2.1, or I'm sorry, 1.1 is just all about functions. And it's just going to be if something's a function or not, yes or no, kind of questions in the homework. Section 1.2 is all about domains and ranges. But before we start talking about domains and ranges, I want to review interval notation. So this was something you probably would have used last year in the Algebra 2 class, right? What is interval notation describing? Well, it actually can be used for more than just domains and ranges. What is a domain and a range? Those are sets. So an interval is going to describe for you a set. What kinds of sets do we use an interval to describe? We use them to describe continuous sets. Like they need to be all the numbers in between, some values, or all the numbers that are bigger than a value, or all the numbers that are smaller than a value. We can't use an interval to describe things like all the odd numbers, because between like 1 and 3, there's infinitely many numbers in between there that we'd be missing. Does that feel okay there? Yes? So, if we have, say, this set, so the set of x is such that x is greater than 2, or greater than or equal to 2. So I often think it's helpful to start with a number line to visualize what this set looks like. So here's 2. Because this is greater than or equal to 2, I know I'm going to have a closed circle because 2 is included in the values. And because it's greater than, it's pointing to the right. Everybody's okay with that? So the interval I'm going to write, the smallest number in that set is 2. And the biggest number in that set is positive infinity, lives at that other right arrow. You could write you just write infinity without the plus sign. I always put the plus sign in there personally, but you don't need to do that. It's clear. Everybody's good so far? The last thing I need to do is indicate whether the lower bound is included in that set. Does 2 satisfy the parameters for that set? Yes. So it should be included. To indicate that it's included, we use the square bracket. Positive infinity. Is that actually a number? It's not a fixed value, right? It's just a concept. So in infinity, we can't say is included because there's always a number bigger. It's like what does that even really mean? So it gets the parenthesis. Infinities always have a parenthesis. Everybody's okay with that? So far, so good? Let's say we have the set set of x is such that -5 is less than or equal to x, which is less than 10. Again, I'll start by just sketching a picture of what I got here. So there's my number line, -5 and 10. I always put 0 in there just for reference. -5, we have the closed circle because -5 certainly satisfies that inequality. And at +10, we'd have the open circle. And then everything in between would fit. Everybody's okay there? So when I write my interval then, my lower bound is -5. My upper bound is 10. And -5 should get is that included or not included? Included, so it gets the bracket. And the 10 is not included, so it gets a parenthesis. Okay. So let's say we have that. So we have x is less than -2 or x is greater than or equal to 5. So there's my number line. So x's could be less than -2. So -2 doesn't satisfy that inequality, but everything less than it does. Or x could be greater than or equal to 5. So 5 would satisfy that inequality along with everything bigger than it. Okay, so far so good. So I'm actually going to need 2 intervals to describe this set. So if I look at the interval here, what's the lower bound? -infinity. And the upper bound is -2. And those should both get parentheses, right? And then if I look at the other section, the lower bound is 5 and the upper bound is +infinity. Infinities always get a parenthesis. The 5 should get a bracket. And the symbol I put in between these is the U. That stands for union. That's an operation that exists between sets. Okay, well, let's do one more, and we'll call it good for today. We'll pick up next time. So let's say the set is all the real numbers between -3 and 2, including 2, or 7. So let's draw our number line. So -3, 0, 2, and then 7 out here somewhere are the numbers we care about, right? So everything between 3 and 2, including, or -3 and 2, including 2. So we're not including -3. We are including 2. Or it could be 7. Everybody's okay with that? So we'll start with this piece first.
Good afternoon, Notre Dame. Let's stop for a moment and reflect on our day. Lord, help me bring to mind where I have seen your presence today. Did I see you working through my friends? Or my teachers? Or my family? God, I pray that you work through me to be evidence of your presence to those around me. Have a great day, Notre Dame, and God bless.
One quick sec. I want to finish this idea right before you guys go, okay? We still have this piece. Is that piece continuous? No, it's just a single solitary value. How do I describe that? I use the set brackets, which is the 7. Is everybody okay with that? All right, you guys should be able to do up through 1 through 4 from section 1. That would be part of Sunday's problem set. If you didn't finish your Delta Math, you should finish that up tonight if you didn't get that done in class today. Have a good day, and we'll see you guys again on Thursday.